Hello, everyone! Today, we begin a fascinating chapter called Measuring Space, Perimeter, and Area. Why does a runner in the outer lane of a circular track start ahead of a runner in an inner lane? The finish line is the same, yet their starting positions are different. The reason is geometry. A path farther from the center of a curve is longer. The staggered starts compensate for this difference, ensuring that every runner travels the same distance. This simple observation leads to a fundamental question. How can we measure the length of a boundary, and how much space does that boundary enclose? For straight-edged shapes, perimeter is found by adding the lengths of their sides. But a circle has no straight sides. Its circumference has a remarkable relationship with its diameter. No matter how large or small the circle, the ratio of its circumference to its diameter remains constant. This constant is pi, giving c equals 2 pi r. But pi is more than a number to substitute into a formula. The chapter traces how mathematicians estimated it by comparing circles with polygons. Archimedes went further, using polygons inside and outside a circle to trap its value between two bounds. We also encounter a deeper fact. Pi is irrational. It cannot be expressed as the ratio of two integers. Now consider only part of a circular boundary. If an arc subtends an angle, theta, at the center, it represents the fraction theta over 360 degrees of the complete circumference. Therefore, L equals 2 pi r into theta over 360 degrees. This idea helps us measure curved paths and leads naturally to the chapter's intriguing problems, puzzles, and paradoxes on perimeter, where familiar geometric intuition is put to the test. But measuring a boundary tells us only part of the story. What about the space inside it? Area begins with a simple unit, a 1 by 1 square. By rearranging a parallelogram without changing its area, we can obtain a rectangle, leading to A equals BH. And here, the perpendicular height matters. Keep the side lengths fixed, but change the angle between them, and the height changes, so the area changes too. Two congruent triangles can be joined to form a parallelogram. Each triangle, therefore, occupies half its area. But what if the height is unknown, and the only information available are the three side lengths? Heron's formula solves this problem using only those lengths. If S equals 1/2 into A plus B plus C, then A equals square root of S into S minus A into S minus B into S minus C. The same exploration takes us beyond triangles. Four side lengths do not always determine the area of a quadrilateral. But when the quadrilateral is cyclic, Brahmagupta's formula provides its area. Remarkably, the chapter shows that Brahmagupta's formula generalizes Heron's formula. The chapter also takes us into ancient geometry through squaring a shape, constructing a square having exactly the same area as a given shape, an idea associated with Bodhayana's geometry work. Finally, we return to the circle, this time to measure the space it encloses. Imagine cutting a circle into many thin sectors and rearranging them. As the pieces become thinner, they approach a parallelogram with base pi r and height r, hence A equals pi r square. From this foundation, symmetry gives us the areas of semicircles, quadrants, sectors, and segments. From a runner's curved path to the geometry of a circle, measuring space reveals a remarkable network of ideas, where lengths, areas, symmetry, transformations, and patterns come together to describe the world of shapes.